Okay, class, howdy. This is going to be our recorded lecture for Wednesday, March 17th. So last time we left off with our discussion of biochemical oxygen demand. We discussed the different terms to describe BOD, and we also discussed the typical BOD5 test. So just to review those, in our analysis of BOD, we said that L sub T is equal to the BOD that is remaining in the system at time T. So if we were to sketch what this looks like, we have L of T that looks like this. Now, there's some initial value that is at time 0, and this corresponds to the ultimate BOD. The ultimate BOD is essentially if all of the biological organisms oxidized all the organic matter they could, this is what the BOD would be. This doesn't mean that they oxidize all of the organic matter, because there's some that the organisms just can't chew up, but all of the amount that they can, they do. The BOD sub T is equal to the BOD that has been exerted at time T. That is how much of the BOD has been oxidized by the microorganisms. This is, a lot of the time what we're interested in, because this BOD sub T is a measure of oxygen consumption. L sub T is how much BOD remains. Overall, we actually don't care about that all that much. What we're more interested in is how much oxygen will be consumed in the system. And that's measured by BOD sub T. And that's going to look something like this. As time goes to infinity, BOD sub T will approach L naught. And actually the mathematics for this works out so that BOD sub T is equal to L naught, 1 minus e to the negative kd times T. And L sub T is equal to L naught e to the minus kd times T. Now this kd is our first order biochemical oxygen demand rate constant. It basically describes how quickly the microorganisms utilize that BOD. Now there was some special significance attributed to this BOD5 value, because this is the value that's used in pretty much all regulations for discharge of oxygen demanding material, whether it's an industrial source, municipal treated wastewater, or something else. Those discharges have to meet a certain BOD, and that's after a 5-day period. So BOD5 is the amount of BOD that has been exerted at 5 days in a standardized BOD test. And so what this actually is, I'm going to move this, since I have some time. Just going to move that over here, and whoops, I forgot that. So the standardized conditions are 20 degrees C in the dark. And there are certain requirements. We must have a change in dissolved oxygen greater than or equal to 2 milligrams per liter. And the DO at the end must be greater than 1.0 milligram per liter. And this relates to the sensitivity of the measurement. So what we're going to do today is we're going to take this kinetic information and explore it a little more. We're going to look at what factors influence KD, the utilization rate constant, and we're also going to explore how we can incorporate these kinetic models into predicting our oxygen sag curve. All right, so here we go. So to start, what factors influence the rate constant? Now, this isn't a microbiology class. If you guys are environmentals or you end up taking our microbiology class, you're going to learn probably a little more about this. But the basic idea is you guys have all had some sort of high school biology, and it's important to recognize that the microorganisms are using this BOD as a source of carbon. They're using it for food. And so several factors are going to affect how quickly they can do that. First is the nature of the waste itself. How amenable is the waste to biodegradation? So I don't have this organized maybe as well as I'd like, but for example, if I compare something like glucose versus, I'm going to pick an example that might not make a ton of sense to you guys, but I'll explain it. So glucose versus this halogenated organic compound. This is a simple sugar. This is a halogenated organic. Ask yourself, which one is going to be more easily amenable in biodegradation? If you're thinking glucose, that's definitely the intuitive answer. And in wastewater treatment trains, the organisms are going to have a more difficult time utilizing halogenated organics as a source of carbon. There are some special organisms that do this, but overall, this type of waste is less amenable to the microbes. Some other examples might be things like benzene. I think your book gives another example, maybe benzaldehyde. Some of these organic compounds like this are not as readily utilized in the microbial metabolism. The second is the ability of the organisms to use the waste. So that is, how good are the microbes at eating the organic matter? Some organisms are going to be better than others. In wastewater treatment, we're continually acclimating the organisms to the waste that's coming in. And so the microbial community gets optimized to remove that waste, and the rate constant will be faster. In a stream there's a mixture of organisms, and they may not be able to utilize the waste as well because they're not as optimized. They haven't been selected to remove that waste. So the organism structure, basically the types of individual microbial species that are present. And one that we can understand a little more readily actually is temperature. We know that in general, temperature influences the reaction rate of chemical reactions, but this is also true for microbiological reactions. And there's some level of prediction that we can make for this. As temperature increases, the microbial metabolism also increases. So as the microbial metabolism increases, the rate of oxygen consumption also increases. Therefore, the rate constant for DO utilization and BOD attenuation increases. It can be described by this equation. This K sub T is K at unknown temperature. So this is not unknown temperature, but non-20 degrees C temperature. And this value is K at 20 degrees C. As temperature increases, the rate constant will increase, and it is sort of proportional to this theta value. Theta has some well-defined measured values, and these are pretty arbitrary if you think about it, but this 1.135 works best for temperatures between 4 and 20 degrees Celsius. And this larger value works best between 20 and 30 degrees Celsius. Now, this isn't something I expect you to just memorize or know. If you needed to do a calculation, you could find this information, or I would give it to you. But the take-home message here is that and I'll also note that these values apply to municipal treated wastewater. And these values will come from a number of studies, with different microbial communities and these wastewaters that sort of average out to this value. So this is applicable to that scenario and can be used in modeling the DO utilization rate constant. Okay, so those are the factors that influence the utilization rate constant. The one we can describe quantitatively is temperature. The others are more just a conceptual understanding at this point. You may learn about it more in future classes. So before we actually focus on the oxygen sag curve, I want to talk briefly about carbonaceous versus nitrogenous oxygen demand. So far we have really only been discussing CBOD, that is the carbonaceous part, but there's many other compounds that also consume oxygen. Some examples include inorganic nitrogen, things like ammonia and ammonium, and then organic nitrogen. And think about in wastewater, where does nitrogen come from? Well, you may be familiar with this compound, urea. You can guess where that comes from. And urea in water hydrolyzes to form NH3 and other products. You can see that the ammonia part is, contained within this molecule. You don't have to know this reaction particularly, but if you've taken some organic chemistry, you might recognize that this is a hydrolysis reaction. All right, so there is certainly a source of nitrogen in wastewater, and this is actually one of the things we really need to remove because nitrogen is a nutrient. It's something that we limit in wastewater discharge. We'll cover this more in Unit 6 within engineered systems. This includes nitrification, denitrification. The overall reaction steps are shown here. In engineered systems, we utilize microorganisms in engineered ways to speed up this reaction. So we take advantage, so to speak, of the organisms. But in the natural environment, things just, you know, happen the way that they do. The ecosystem might shift to continued input of certain conditions, but it has to deal with this nitrogen that's being released. And so the way that that happens is through this nitrification process. Here, nitrogen in the form of ammonia. This is a very reduced form of nitrogen. Gets oxidized to nitrate. So this is the nitrification part. Later on in an engineered system, you have denitrification, in which the nitrate is converted to nitrogen oxide, which is a gas and can evaporate out into the atmosphere, or N2, which also goes back into the atmosphere. Now, the theoretical NBOD, we're not going to talk too much about this, just give you the definition. It's going to be the grams of O2 that are utilized divided by the grams of N oxidized. So if I had to kind of give an example here, if I look at this overall reaction, you'll notice that 2 moles of oxygen are being utilized for every 1 mole of NH3. Therefore, 2 moles of O2 divided by 1 mole of NH3 is related to my theoretical oxygen demand, but typically the theoretical amount is in grams, not a mole ratio. So I need to account for this. There's 32 grams of oxygen for every mole of O2. And there's 17 grams of ammonia for every 1 mole. Oops, got that wrong. 1 mole of ammonia has 17 grams of ammonia. And then I can see that my moles cancels out. And I'm left with 4.57 grams of O2 per gram of NH3. That would be my theoretical oxygen demand. Now let's take a look at actually what this might look like in comparing NBOD versus CBOD. This plot shows oxygen demand in milligrams per liter versus time. This curve here shows the carbonaceous biochemical oxygen demand, and this is typically what we saw in our previous slides. So if we're only considering, say, to here, that kind of looks like what we've seen before. And part of this is because what we'll call nitrifiers, those organisms that convert ammonia to nitrate, tend to be slow. They don't grow super quickly. And so it takes some time for them to really catch up and start growing. And at that point, the oxygen demand will increase as the nitrifiers start growing. So another way to think about this is NBOD kicks in as nitrifiers enter the growth phase. This initial part we could call like a lag phase. They're not growing very quickly. All right, so hopefully that gives you a good qualitative understanding of NBOD versus CBOD. Now what we would like to do is predict this oxygen sag curve. So that's what we're going to focus on next. All these are very specific learning objectives, and so I encourage you guys to use this as a study guide. We will address all of these throughout the rest of this unit. The big picture, again, I've said this before, and so I feel like I'm repeating myself, but ultimately what we want to do is to be able to model the DO attenuation and then rebound within a stream. So how do we do this? Well, we're engineers. We've learned about our mass balances. We like mathematical models. So I think we have all the tools to do this. I'm going to take the time to show you the two different ways of deriving this. If you're an environmental engineer, the second way is kind of the better way, and you'll probably use that approach in other classes. The first way is a little more simplified and just is based on our mass balances. So let's start with the first one. So I'm going to take this picture and sort of condense it down into a simple figure. In this figure, the blue water represents our clean, high dissolved oxygenated water. Here, this sort of darker yellow brown color represents the waste that is getting into the water. The shading kind of gives you an idea of the intensity. So as the waste gets mixed in, the DO decrease is greater at a certain point and then rebounds. Now in our mat, we're going to do two mass balances. The mass balances that we're going to do are first over this mixing point, that's in red. And then we're going to do the downstream river. And in this mixing point, so let's say I have a waste stream right here. This is not a good color. So you have a waste stream right here. It's on the side of the river. I am just going to tell you this. If you learn about it in a later class, you can mathematically prove that this is true. But what's going to happen is, let's say it's being released at the side of a river. You're going to have mixing across the river very quickly relative to how quickly it gets distributed downstream. And so what we're going to assume is that we're going to assume that there's complete mixing across the stream. That is from, say, the side to the other end prior to significant transport downstream. Oh, that's kind of cool. Nope. In order to complete this model, we need to consider the different sources of oxygen within the river. There's different sources. Those include the atmosphere. Oxygen's getting in from the atmosphere. Those are there's photosynthetic organisms. We're going to actually ignore this one in our calculations. This one is pretty easy to account for through Henry's law. How is oxygen consumed in the river? Now, there's cellular respiration. There's also BOD. This is the oxygen demanding material. And this is the one we're going to consider. We're going to ignore this one. All right, our assumptions, just to formally say this, we're going to ignore photosynthesis and cellular respiration. So we're just going to think about the physical processes, and also we're going to focus on the bulk microbiological processes involving BOD utilization. And this assumption is justified because these are small in comparison. Another assumption, just to again make sure it's written down, is that we're going to assume that there's complete mixing. We're also going to assume no BOD O2 utilization at the mixing point. Only when waste starts traveling downstream. And the idea here is that, I'll come back to this in a second, the idea is that the mixing happens relatively quickly in this regime. And so there's not going to be much utilization here. But then once it's mixed and starts traveling, that's when we start taking into account the oxygen utilization. All right, so in our mass balance, we have we have a few different things to consider, right? We have our upstream water, we have our waste going in, and then once those are mixed, we have our PFR, and that's moving out of this control volume here. So if we label all of these, we have to think about the BOD remaining, which is L. We have to think about the dissolved oxygen. That's ultimately what we want to know. And we have to think about the flows. In the terms of the PFR, we're going to think about it in terms of position as well as time. Now these labels tell you what each of these are. What I've done here is created an x coordinate, and so defined this position as x equals 0. So we're saying that mixing happens at x equals 0. There's a control volume where that mixing happens, and then after mixing, it starts traveling downstream. Subscript R corresponds to the river upstream of the waste discharge. W corresponds to the waste. And then mix, you might guess, corresponds to the mix system downstream. All right, so let's do our mass balance on the mixing point. If we assume that oxygen is conserved in the mixing zone, meaning that it's not going to be utilized by the BOD, our mass balance on the DO looks like this. We have QR, DOR. Again, just to highlight it, we're focusing on this control volume right here. So we have any DO that's present in the upstream. We have the DO that's present in the waste. We have Q mix, DO mix. And the accumulation within this control volume, remember, is equal to the change in, technically this is mass actually, not concentration. But we're also going to assume that the system is at steady state. We can model waste discharges approximately as a steady state, assuming that over, the days, weeks, months, there's a nearly constant BOD entering the stream. Solving for DO mix, we get something that looks like this. This should be pretty familiar to all of you. We're just taking the DO and the waste and then the river and then dividing it by the total volume. So what's the dilution of the DO into the downstream volume? Now we can do the same thing on L. And if we do that, we get L mix is equal to QW LW plus QR LR divided by Q mix. All right. Now we've done our mass balance on the mixing zone. So next we want to do the mass balance on the river. We're going to model that system as a plug flow reactor. To do this, we're going to assume again that the waste source is constant, so the system is at a steady state. Question for you guys to think about. Does this mean that the DO as a function of distance is constant? If you're thinking about this, the answer is no. Clearly, DO is changing as we go down the stream. It's decreasing and then increasing again. But again, the steady state assumption is for a PFR does not result in a no change in concentration because the control volume is our individual parcel of water. Another assumption that we're going to make is that the rate of deoxygenation is coming from the BOD test, right? The whole point of our BOD test was so that we could get this oxygen utilization rate, and we're going to use that value within our models. Another assumption is that DO disappears due to microbial action and that this rate is proportional to the BOD remaining. This is basically the way that we developed the kinetic expression for L. Okay, so if we put those things together, what we're going to see is that dm dt is going to be equal to two parameters. I'm going to have within, remember, all right, so taking a step back, dm dt, this is for my plug flow reactor. I'm going to have two things happening here. I'm going to have a negative reaction term. This is O2 consumption by the microbes, which is equal to KD times LT. The second term is our re-aeration term. And this is due to O2 from the atmosphere. All right, so dmdt is equal to this negative reaction term plus the re-aeration. Remember, in a PFR, we don't have mass flowing into the control volume or out of the control volume. And so there's just the reaction terms. In this case, there's sort of two terms, right? We have the negative reaction and then the reaeration. So to revisit, we remember that this can be described by L sub t is equal to L naught e to the negative k dt. This is the kinetic expression that describes the amount of BOD remaining at time t. Let's also remember that this t is related to the river velocity. By position divided by the velocity. So we can do a variable substitution here. Okay, let's see, I think I'm going to cut it off there for today. I will post the other lecture in a separate Zoom video.